the Wellness Day on Wednesday, so we got bumped back a day. Does anyone have any questions about the announcements? No? All right, cool. Is there anything in the chat, Emma? I guess I can't see the chat from my view.
No. Someone just said no.
Cool. All right, here's just a quick note on problem 3 of the Wiley problems on the homework. You get this you have this weird shape of water that's like the leftover from a quarter circle, and you need to find the centroid of that. So, in Cal 2, you learned through calculus how to do something like this, but that's not really necessary for this class. So here is a good resource to look up. It has a whole bunch of centroids here. It has an equation for getting, that obviously is derived from doing some calculus to find that centroid. So there's probably other ways to find it too, but this is just a really easy way to find that because it's just such a strange shape that it wasn't in the notes. So I thought that might be a little bit of help on problem 3. All right, let's start with today's topics, which are buoyancy and stability, and I'll give it to Emma. Do you want to share, Emma? Should we stop?
Yeah.
Okay.
Can you put the link in the chat, Alexi? Oh no. For that centroid thing.
Oh yeah. I'll do that. Yeah.
Cool. Okay. So hopefully we'll get to PowerPoint soon. Take a little second. Awesome. Oops, this thing is slow today. Okay. Cool. So we're doing buoyancy today, which is kind of cool because buoyancy is really intuitive, and usually people's intuition about it is actually like how it works. So it's basically like if an object will float and if it will be stable when it is floating and how it is floating. So Archimedes' principle is any object wholly or partially immersed in a fluid is buoyed up by a force equal to the weight of the fluid displaced by the object. Okay, so here we have 2 cubes. One of them is fully submerged in water and one of them is partially submerged. For each cube, the force buoyancy is going to be the specific weight of the fluid. So I'll just write it out. Times the volume displaced. And then the weight is what it always is the gamma specific weight of the object times the volume of the object. Just so you know what those symbols are. And then for both these objects, one thing that we do know is different about them is that the volume displaced is different for each of these objects in the water. For the first one, the volume displaced is this whole entire volume right here. It's the whole entire cube. But for the second one, only this volume is displaced, so it's a little less. So that's one thing we know when looking at this picture. Okay, so now we're going to derive the equation for that centroid thing.
Oh yeah. I'll do that. Yeah.
Cool. Okay. So hopefully we'll get to PowerPoint soon. Take a little second. Awesome. Oops, this thing is slow today. Okay. Cool. So we're doing buoyancy today, which is kind of cool because buoyancy is really intuitive, and usually people's intuition about it is actually like how it works. So it's basically like if an object will float and if it will be stable when it is floating and how it is floating. So Archimedes' principle is any object wholly or partially immersed in a fluid is buoyed up by a force equal to the weight of the fluid displaced by the object. Okay, so here we have 2 cubes. One of them is fully submerged in water and one of them is partially submerged. For each cube, the force buoyancy is going to be the specific weight of the fluid. So I'll just write it out. Times the volume displaced. And then the weight is what it always is. It's the gamma specific weight of the object times the volume of the object. Just so you know what those symbols are. And then so for both these objects, one thing that we do know is different about them is that the volume displaced is different for each of these objects in the water. For the first one, the volume displaced is this whole entire volume right here. It's the whole entire cube. But for the second one, only this volume is displaced, so it's a little less. So that's one thing we know when looking at this picture. Okay. So now we're going to derive the equation for force buoyancy. It's pretty simple, but we're going to show that force buoyancy equals the specific weight of the fluid times the volume of the object when the object is fully submerged. How do I spell submerged? And you can do the same exact derivation for partially submerged, but we're just going to do it for the fully one, and then you guys can just trust us that the equation works, or we can do it later if you really want to. Okay, so we're going to do a little free body diagram. Here's an object underwater, fully submerged, and we're going to think about all the forces that are acting on the object. So I won't make you say them in the chat, but we have the weight, and then we have a force pressure from the water going down and a force pressure from the water going up. And then we have these horizontal pressures. But as we've talked about in previous classes, those horizontal pressures are equal and opposite, so they cancel out because they're at the exact same height or depth in the water. So force pressure, we're going to call this first force pressure 1, and forces from pressure is always going to be pressure times area, and we'll call that pressure 1, and then this one will be pressure 2 times area. And we have to think about what we were talking about yesterday, where you think of the area by pretending that you are the force and that you're looking at the box. So pretending that I'm this force right here and I'm looking at the box from above. So the area is just the area of this right here. Or for force pressure 2, it's the area right here. And because it's the cube, the areas are the same. So I'm not going to give them area 1 or area 2. So force buoyancy is actually just like a little shortcut word, or like another word for both of these force pressures. So it's just like another name for them, and it makes it easier so we can talk about it. So force buoyancy is going to equal, let me make my axes, is going to equal, it's going to equal pressure 2 area in the positive direction minus pressure 1 area. So it's force pressure 2 minus force pressure 1. But I just went ahead and changed it into what those force pressures are. And then we can simplify this even more to make force buoyancy area times pressure 2 minus pressure 1. Okay, let's try to figure out what pressure 2 times pressure 1 are, because those aren't just usually givens in a problem. From hydrostatics, I think it's page 9 of the notes. We went over this a little bit ago, but we know that pressure 2 on this box is going to equal pressure 1 plus specific weight of fluid times height, if this is the height. So this makes sense, because if we were at this pressure and we wanted to get to the pressure at point 2, we would add height times gamma, because pressure increases with height proportionally to gamma. So we have that equation. Okay, and then this don't want to change my colors. This can turn into pressure 2 minus pressure 1 equals specific weight of fluid times H. So we're going to substitute this into here and get that force buoyancy equals area times specific weight of fluid times height. You guys probably know this, but if we're looking at a cube, and this is the area, and this is the height, area times height equals volume. Remember that weird bead. So we can turn this into force buoyancy equals gamma fluid times volume of the object when it's fully submerged. Nice. Any questions? Cool. It's like one of the easier things hopefully you guys learn this class. Okay, so we're going to do like a little write out on if something will float or not. Again, this is super intuitive, but we're just going to write it out. So if we had a box in water and we have our force buoyancy going up and our weight going down, we know intuitively that if force buoyancy is greater than weight, the object's going to float, and if it's less than weight, the object will sink. And because we just care if it will float, we don't care if this box is partially in water, so I'll make my forces, or fully in water, but because the equation for force buoyancy, like the always equation for force buoyancy, is specific weight of fluid times volume displaced, and when this thing is fully submerged, the volume displaced is bigger, we're going to think about if it will float only if it will at least float when it's fully submerged. So we want to care, will this at least float if it's fully submerged, not if it also will float if it's partially submerged. So I'm going to turn this equation into a fully submerged equation where it's specific weight of fluid times volume of object. Hopefully this will make more sense as we keep going. And then the weight equation is what it always is, which is the specific weight of the object times the volume of the object. And so as we decided, it will float if, we've already decided that if FB is greater than W, so that would be the same thing as if the gamma, the specific weight of the fluid times the volume of the object is greater than the specific weight of the object times the volume of the object, because those are the equations right there. And then we can cancel out, I'll give you guys the little weird B's so you get used to them because they're weird. So then we cancel out the volume of the object and we get specific weight of the fluid is greater than the specific weight of the object. It will float if this is true. Because on page 1 of the notes, you can see that gamma equals density times gravity. It will also float if the density of the fluid times gravity is greater than the density of, oh no, hopefully it won't take forever for that to pop back up. The density of the fluid times gravity is greater than the density of the object times gravity. Cancel that out. It will float if the density of the fluid is greater than the density of the object. You guys know this, probably. If you're in a swimming pool, if you put something in the swimming pool that has a greater density than that water in the swimming pool, it's going to sink. So this was just writing it out more. Any questions on that? Cool. Tell me if I am going too fast through this slide. I'm going forward. Okay, we're going to do an example that Alexi thinks doesn't make any sense, but it does make sense and it's cool. So, when the Truncated Dam was constructed in northern Brazil, the lake that was created covered a large forest of valuable hardwood trees. It was found that even after 15 years, the underwater trees were perfectly preserved and underwater logging was started. During the logging process, a tree is selected, trimmed, anchored with ropes to prevent it from shooting to the surface like a missile when cut. Assume that a large tree can be approximated as a truncated cone with a base diameter of, so here's our tree. Oh no, it's so ugly. With a base diameter of 8 feet and a top diameter of 2 feet and a height of 100 feet. Determine the resultant vertical force that the ropes must resist when a completely submerged tree is cut. The specific gravity of the wood is approximately 0.6. Cool. Here is the dam right here, and here's a cool underwater forest. So if we think like, pretend this tree right here is completely underwater, and they're cutting the tree, and then it's shooting up because it's so buoyant, so they need to make ropes that are keeping the trees down so it doesn't shoot up like a rocket. Okay, so what are we going to do first? We're going to make a free body diagram, because that's what we always do. So, where am I going to make it? I guess I'll make it here. So here, no, I don't like that. Okay, so here is my tree. It's a truncated cone. I'm going to call this radius right here. Well, I guess that radius equals 1 foot. but they gave us the diameter, which is 2 feet. And then right here, radius 2 equals 4 feet because the diameter equals 8 feet. And then what are the forces on this tree when it's completely submerged in the water? Because this is before it shoots up like a rocket. So we got weight on it, and then we got force buoyancy, and then we got this like force ropes. Okay, so then we make our equation. All the forces in the y equal or is equivalent to, gotta make my axes so we know it's positive, equals force buoyancy in the positive direction minus weight minus force ropes equals 0. Okay, do our little thing. We don't know what this is. We can solve for this and we can solve for this. So what do we do first? Weight sounds easier. Okay, so weight equals what it always equals a lot of times in this class, so it's not always, but the specific weight of the tree times the volume of the tree. Specific weight of the tree was given. Oh, well, specific gravity was, and we can get specific weight from specific gravity by multiplying it by gamma H2O. So we're still good. But we need to find the volume of the tree. Y'all are super resourceful. So you're going to Google that for a volume of a truncated cone. The volume of a tree or of a cone is pi h over 3 r1 squared plus r1 r2 plus r2 squared. So we're going to do this really fast. We're going to get pi times 100 feet, which was given, over 3 times r1, which is 1 squared plus 1, oh shoot, I forgot my, times 2 feet, I forgot my units on that one, plus 2 feet squared. Feet squared. Okay, now, I could do that really fast. I don't really, oh my gosh, this is not right. No one put it in the chat. You didn't catch me? That should be 4. Because the radius is 4 feet. Okay. So, I'm going to pretend I'm doing that on my calculator. And then, your volume that's going to come out is volume of the tree equals, what is FR again? That's force from the ropes. Volume tree is, okay, 2200 feet cubed. Awesome. So, why did I put it there? Oh well. So this is going to equal 0.6 specific weight of tree times 62.4 pounds per feet cubed. Specific gravity of water times volume tree, which is 22 or whatever, 2,200 feet cubed. Cancel those out, and we're going to get that the weight of the tree equals, I guess I could do this one, it's not that difficult, 62.4 times 2200. Okay, we're going to get 82,368 pounds. Awesome. So we have weight. Yay. Now we just need to find force buoyancy, because that's another one we can solve for. Maybe I can do this all on one page. Force buoyancy, because it's completely submerged, is also going to be specific weight, or it's going to be specific weight of H2O, which is the specific weight of the fluid, times, okay, I'm actually going to do this out. Okay, specific weight of fluid times volume dispersed, and in this case, that's going to be specific weight of H2O times the volume of tree, because the tree is completely submerged, so that's the whole displacement. So this is going to be 62.4 pounds per feet cubed times what we found earlier, which is whatever this number is, times foot cubed. We're going to do that really fast. Hopefully I'm not missing something. And that looks good. So we have 137,280 pounds. So 137,000 pounds. So
I think the volume of the tree might be wrong.
Really?
I don't know if you switched the second R2 to 4 feet.
No. Yeah, it needs to be 4 feet. Nice call. See, it's a good thing I didn't do it on my calculator, because then I would have gotten the right answer. So it is still this, I promise. Maybe I'll actually do it out of punishment for my confusion. Times, okay, 4 squared plus 4 plus 1. Nice. Okay, you'd actually get 2199, which we should, okay, I'm going overboard on this problem. Okay, so now we have force buoyancy equals 137,280, and because from over here, from this equation, we can say that F ropes equals force buoyancy minus weight. We can say F ropes equals 137,280 minus 82,368 pounds. Gotta put pounds. Even though I don't put pounds, you have to put pounds. Okay, cool. So you're gonna get that force weight equals, I guess I could do it. 137,280 minus 82,368. 137. Okay. You get 54912, and then you see, okay, unfortunately this problem has just one sig fig, which everyone hates. So I guess it'll be 50,000 pounds of R equals. Very cramped. Nice.
I just have one question.
Yeah.
So how are all the sum of the forces equal to 0 if the tree isn't the tree moving?
We're trying to stop the tree from moving. So if the rope wasn't there, it would shoot up, but they're trying to have ropes so that the tree's not moving. So we need these ropes to be strong enough so that it doesn't go up.
That makes perfect sense. Yeah.
Why is the specific weight of the tree the specific weight of water? Okay, force buoyancy. So this guy, force buoyancy, use specific weight of the fluid. For weight, we're using specific weight of the tree. So that's how it will always be. So the weight is going to be specific weight of the object times volume of the object. Hopefully that makes sense. The specific weight of the tree. Oh, if you're talking about this, we can turn by using the specific gravity, you can multiply a specific gravity of water times the specific weight of, I think I'm messing this up. This should be, I got my things messed up. But anyways, I can multiply this 0.6 times the specific gravity of water, right? That's what it's called. No, I can multiply it by the specific weight of water to get the specific weight of the tree. Hopefully that makes sense. So this should actually be a G. This is SG, I think. Yeah. Cool. Okay, Lexi's going to take it away. He's going to talk about a problem if it's not fully submerged.
Yeah, so, and I would say that Emma's example was really cool once I actually saw it. So we're going to kind of continue on. I'm going to do another example. Just give me a second here. I have to share the screen. Everything went dark.
And your camera's not on right now.
Yeah, I know.
Or your cool one.
Give me a second. I guess, if anyone has any questions about that previous problem, they can ask it now. All right. Share it over here. Okay. All right. Can everyone see that? All right. So now we're going to do an example as if the log has floated to the surface, but we don't actually know its specific weight. So that's kind of the goal of this problem, is to figure out what the specific weight of the log is. However, we know how much it's floating on the surface. We know how much of the log is underwater, and we know so we know 1/4 of the log is. Ooh, I gotta get my little drawing tool on. We know that 1/4 of the log is above the surface, and 3/4 of the log is below the surface. So I guess if we read out the question: a freshly cut log, and we'll say it's from the bottom of this reservoir, with 1/4 of its volume protruding above the water surface. Determine the specific weight of the log. So first we can draw a specific body diagram like we always do. This one's going to be pretty simple. We have our log. It's not quite exactly the same, but we're going to have the weight force going down. We have centroid of the weight that's going down. We have a weight force going down, and then we're going to have a force buoyancy pushing up on the log. So pretty simple, but we should still draw a free body diagram just to make sure we understand what's going on. So let me go to the next slide. I have that free body diagram drawn there. So from this free body diagram, we can see that there's two forces. We can do a sum of forces in the y direction, which is going to be negative weight plus force buoyancy. So we can say that the force buoyancy is going to equal the weight. And then from what we learned earlier in this class, we know that the force buoyancy is going to be equal to gamma H2O, or gamma water, times the volume that's displaced. So we'll call that DIS, volume displaced. And then the weight is going to equal gamma of the log times just the whole volume of the log. So we can say that as volume log. All right, so if we rearrange this equation, we can get that the gamma log equals gamma H2O with the volume displaced, and we'll make those the V's like we were before, volume displaced divided by volume total. Now in this problem, we know that the total volume is 1, right? If this is 1/4 the volume and this is 3/4 the volume is underwater, we can say that the total volume is 1. So we can have this be equivalent to, and this shouldn't be an equal sign, this should be a multiplication sign, sorry about that. This should be equal to gamma H2O times 3/4 volume, the total volume over, so the volume displaced is 3/4 of the volume of the total volume. The total volume's on the denominator here. So those two volumes are going to cancel. Oop, I guess that kind of worked. So then we finally get gamma log equals 3/4 gamma H2O. And that's pretty easy. We've done that. We know what gamma of water is, and I guess this problem doesn't specify the units, but we're going to do it in imperial units. So we're going to have 62.4 pounds per feet cubed. And then when we do the math, we'll get that the gamma of the log equals 46.8 pounds per feet cubed. So there's our answer right there. For sig figs, we don't have any numbers. We just have these fractions. We'll just assume that those fractions are exact, and that we'll use the significant figures, our 3 significant figures, from our value of gamma water. So there we go. That's how to do kind of a buoyancy problem where some of it's submerged, but not all of it's submerged. So remember that the buoyancy is only if the object is floating on the surface, the force buoyancy is only the volume, the gamma water times the volume displaced, not the whole volume, just the volume that's been displaced by the object. So just that volume that's right here under the water. All right. Does anyone have any questions about that?
The displacement will always be, like the volume displacement will always be the part that's in the water, right?
Yep, it's the volume of the object that's under the level of the water. So like below this line right here at the water surface.
Okay, thanks.
Does anybody have any more questions?
So when does the buoyancy force equal weight? Is that anytime it's floating?
So I guess anytime it's floating, the force buoyancy is going to equal the weight. If the force buoyancy is still going to equal the weight, well, I guess it depends if the object is moving, right? So in this scenario, the object is still on the surface, so like there's two forces acting on it, force buoyancy and weight, and they have to be equal. If the object's under the water, force buoyancy could still equal the weight if it's staying still. If the object is sinking, i.e. it's like vertically traveling downwards, then the weight is going to be more than the force buoyancy because there's going to be an acceleration on the object. So I guess there's kind of two parts of that question is like, what is the object moving or not? So like, is there accelerations involved or is there no acceleration and therefore there's kind of an equal balance of forces? If there's an equal balance of forces, then the weight and the force buoyancy would have to be equal as long as there's not something else like the ropes in the previous example. Does that answer your question?
Yeah. And also, is it always true that specific gravity times the specific weight of water would equal the specific weight of the object?
Yeah, that's the definition of like SG is how specific gravity is how that's. I think you might have been taught it that it's the relation between the density of an object and the density of water, while the specific weight is just the density times gravity. So that relationship will still hold. So specific gravity could also be known as the gamma of some fluid. Well, it doesn't have to be a fluid over gamma water. This can just be any object.
Okay, thank you.
Yeah. All right.
I'm confused on how you go from the line, like gamma H2O times volume displacement, that one, to the next line where you have the displaced volume over the total volume. Like, I don't know where the volume of the log went, basically.
Oh, sorry. Did I make a mistake there?
You just renamed it.
Yeah, it's just renamed it. So volume log equals volume total. For consistency, we can put log right there. Does that make sense now?
Yeah, thanks.
All right, cool. Any more questions? All right. Doesn't seem like we have any more questions, so we'll move on. I'll use my mouse for this. Okay. So next, we're going to talk about stability. So we have this object. In this case, we're also going to be talking about boats and stuff that are floating at the surface, or I guess they could be also underwater. But like, what are they going to do? They might not just sit there. There's going to be some forces on it going in different directions that might cause it to tilt and move around. So in this case, we have like kind of a wide boat, and we have this first example of it kind of sitting normally in the water. And then we kind of, for some force, we don't know what that was, the boat got tilted. Maybe it's a wave or something like that. So now the force buoyancy has moved to the right because there's like more area here, like displacement. See how there's like much more area here on this side than there was now previously, and there's like less on this side. So force buoyancy is moved to the right. So I guess the question that we're going to go through is, will this change in ship tilt cause the ship to tilt more, i.e. an overturning couple, or tilt less, restoring couple? So tilting over, like an overturning, so tilting more would be like it keeps tilting like this direction. So it's like even more tilted, like it's capsizing, or tilting less would be like it goes back to like almost, it's kind of tilting back to go back to the normal, like how it was before. So we don't have actual clicker questions today, but we're going to do questions in the chat, and you can pretend they're for credit. So either let's make it easier for you guys. Let's say 1 is an overturning couple and 2 is a restoring couple. Can you guys put in the chat what do you guys think will happen with this scenario? Are people answering in the chat, Emma?
Yeah.
Okay.
It's funny. It's like not anonymous anymore. It looks like there's a lot of 2s. They might have been like biased into putting 2 though, because a lot of people put it.
Seems like, all right. I don't know. I have a lot of people answered. Should I stop?
Yeah, a lot of people answered.
All right, cool. So you said most people were saying 2?
Mm-hmm.
All right, and that is correct. So we'll go to the next slide. And as we can see with our little drawing here that I cropped out in the previous, we're having a restoring couple. And the reason for that is if we did the sum of the moments somewhere here on the ship, for example, if we did like the sum of moments at point W, like, because, you know, when you do a sum of moments, you have if there's a force directly acting on that point, it doesn't matter. So the sum of the moments at, or we'll call that CG, at the center of gravity would just equal force buoyancy. And in this case, it would be it'd be a positive force because it's going counterclockwise, but more importantly, it's going in this direction, which means it's a restoring couple. It's restoring the ship back to its previous position. So this is what you want. If you design a ship, you want it to have a restoring couple when it tilts so that you don't like tip over and have the whole ship capsize. So that's our next example. Here we have some ship designer that didn't go to engineering school, designed a really tall ship because they thought it would be cool. And we have, as some force, it's caused it to tilt. But in this case, force of gravity is moved to the left, and the force buoyancy is moved to the right. Center of gravity is moved to the right, and the force buoyancy is moved to the left. And I want to make you guys answer this as a clicker question because obviously there's going to be the opposite thing. It's going to, will this change be overturning or restoring couple? In this case, because now if we do the sum of moments again, we would do it at that point. It's going to cause the ship to turn this way, causing it to tip even more, causing this to move further this way. The center of gravity to move further to the left, and the force buoyancy to move to the right, and the force buoyancy to move further to the left, making it even more. So that kind of like a cycle that perpetuates itself, and the ship would slowly tip over and capsize. So let me go to the next slide where there's the overturning couple. Does anyone have any questions about that?
Could you go back 2 slides really quick?
Yeah. To this one right here?
Yeah, that's good. I got it.
Okay, cool. All right, anybody else have any questions? Is there anything in the chat, Emma? All right, cool. We're going to move on, and we're going to just talk about this some more with some different examples. So here, this is kind of a more complex real-life example because, a real ship isn't going to be, it's going to have differences in density throughout. Like its center of gravity isn't exactly going to be perfectly in the middle of the ship. You're going to have the ship is a different shape. You're going to have compartments with stuff in them and open compartments and stuff like that. So example on the left, the forces of buoyancy, a ship So A is a ship in calm seas with the center of gravity and the center of buoyancy positioned marked. So you can see right there. And then on the right, so it's an unstable ship with unevenly distributed density. It can't tilt itself back upright. So in this example, again, the center, like our previous example, the center of gravity is shifted to the left during the tilt, and the center of buoyancy is shifted to the right. And that's making it unstable. Basically, it's going to capsize because it's not a restore, it's an overturning couple, and it's going to go that way and capsize. Here we have, this is what most ships do. They put a ton of weight. Like, I think back in the day for like wind ships, they put a whole bunch of stones, heavy stones at the bottom, but now we have a keel. Modern day ships have a keel, so there's like a whole bunch of weight. So in this case, the center of buoyancy is actually above the center of gravity. And then when there's tilt, the center of gravity hasn't really moved, but the center of buoyancy is moved to the right. But now we have a restorative couple, so it's going to spin it back over in that direction, tilting it back to the upright. So pretty intuitive, but basically this is kind of why you have the keel of the ship, so that make sure that you have that restorative, I'm going to spell this wrong, restorative couple, as well as overturning couple. Even though they're in the, remember the restorative and overturning couple, like the direction they spin doesn't matter because it's just whether it's pushing it back upright or keeping it tilting over. All right, does anyone have any questions about that? Doesn't look like it. All right, let's continue on. And how much time? We have quite a bit of time. All right, so here is just kind of a fun example. We have a cargo ship. I found this off the internet, and it's obviously seen some difficulties. You have all of these containers moving to the right, kind of tilting. So they basically are moving the center of gravity. This is not what you want. You don't want the center of gravity to get like moved over because of all these cargo. It's tilting over, so that's going to cause a big overturning couple to the right because the force, the center of gravity, we'll call that, like, it's kind of hard because it's a 3D example, but the weight is here at the center of gravity, that's moving to the right, so that's going to keep pushing it over, so it keeps tilting, and eventually it's going to capsize, which is probably what happened to the ship. And all of your goods that you ordered on Amazon are now at the bottom of the oceans.
I already planned on it.
All right, so we're gonna do one more example here. If the center of gravity is above the center of buoyancy for a completely submerged body, is this a stable or unstable equilibrium position? So I drew a little figure here already. So we have force, buoyancy, and the weight. So is this a stable or unstable position? So put your guess in the chat for participation points, even though they're not real, but we're going to pretend they are, so you guys get something out of this class.
Yeah.
Yeah.
Let me ask you.
Go ahead and type that in the chat.
Do you want what do you want
It's a lot of responses.
All right, Emma, what's the consensus in the chat look like?
It looks like the majority are saying unstable.
All right, so that is correct. This is unstable because, again, actually, I think if we did the sum of moments, we could do it at either point. But if we do the sum of moments here, right, the only force we're going to have this force going down. It's going to be pushing it around so that it basically spins in the water so that it wants the specific gravity where the weight is acting to be below the force of the buoyancy when it's underwater. So we can go here, the solution. The center of gravity is above the center of buoyancy for a completely submerged body. This is an unstable equilibrium position. So, I guess I'll draw another one here so if we have another body, let's say we have the force buoyancy going up from here, and the weight going down from here. So let's say they're even like this. That kind of looks stable, but they're never going to be perfectly aligned. Weight's always going to be a little bit on that side or a little bit on that side, and whichever way it is, it's either going to cause it to rotate that way or rotate that way. So it's kind of unstable. If we have a different object and we have the force buoyancy above the weight, like this, it's not going to cause it to rotate because the force buoyancy is pulling it up, the weight's pulling it down. So there's not going to be, like, I guess, if let's say the force buoyancy is like a little bit over here, it's going to, like, if you did the sum of moments, it's going to want to rotate a little bit there to stable position, which is going to make it, like, it's going to move the force, you know, stuff's going to move back over there. So it's going to go back to stability instead of position like this, where it's going to keep wanting to turn over and basically go upside down. So does anyone have any questions about that kind of basic conceptual stability problem? Anybody in the chat? No? No? All right, you guys don't have any questions today. That's okay. All right, seems like we got through lecture a lot sooner than, quicker than normal because there wasn't a ton of topics for today. So I guess we can finish with, does anyone have any questions about the class, or maybe we can also go over some questions about the homework if people have that as well.
Yeah, so you guys can leave, but if you have any homework questions or whatever, you can stay.
When's the first exam?
Oh. We can figure that out.
I think it's
It might
next
be
week.
different.
It should be next Tuesday.
Yeah, I'm pretty sure it's Tuesday. Also, thank you.
Welcome.